Right, we've got a worked example here in the forces section. This problem is essentially a system of particles. It's a little bit untypical because the nature of these things normally is that we might look at the motion of the two particles that share a common acceleration and use that in order to find the tension in the string, or we might find the tension and use that to find the acceleration of both particles. So, but this one's a little bit different. So let's just have a look. Now, I think rather than go through this first paragraph, I think we can sort of see these if we've done this sort of thing before. A couple of particles on inclined planes connected by a light inextensible string over a smooth pulley. That's the kind of normal assumptions. The things that are of key note in this first paragraph here is that the particles A and B of identical mass, but we're not told what that mass is. We can see kind of everything else, the angles, the vertical height of B, and then the coefficient of friction between the particles and the planes is 0.15 in both cases. Okay, so what happens? The system is released from rest with the string taut and with particle B a vertical distance of 0.75 meters from the ground. Yep. Particle B descends along the rope until it reaches the ground, at which point it immediately comes to rest. Particle A continues to move up the slope until the forces of gravity and friction cause it to come to rest. Okay. It says momentarily, but we're only interested in that point in time. Find the total distance traveled by particle A between the time that the system is first released and the time that particle A momentarily comes to rest after B has reached the ground. So we've kind of got two parts to our motion. First of all, B falling to the ground and dragging A up with an increasing acceleration. And then that pulling force disappears when B hits the ground, but A carries on. It's got some velocity at that point when B hits the ground, and so therefore it will use that acceleration to climb further up the slope. So we've kind of got two parts to this. Now, if we draw our forces diagram here, so it seems to got a lot of lines on it, but really it's the same for both particles. What we've got is, well, we've got force of its weight there, but that's resolved down the slope, in this case, mg sine 70. We've got the force of friction opposing its motion, which is of course equal to the coefficient of friction mu times the normal reaction of B, or the surface of the slope on B. And that is equal to, well, we've only got these forces acting on this particle in the perpendicular direction. So the resolved part of the way, mg cos 70, is counterbalanced by this reaction force. So the reaction force is also mg cos 70. Okay, so at this point, we're actually not interested in these two anymore. They've served their purpose. And we've essentially got these three that are determining the actual motion of the particle. Well, not just those three. I mean, we've got the equivalent thing on this other side. And so we've got the resolved part of the weight coming down here, and also the force of friction, which is equal to mu times the reaction force. And we've got the same situation here with the resolved part of the weight perpendicular and the reaction force. Right, okay. So that's the setup. As we've seen in the question, the height of B above the ground is 0.75 meters vertically. Okay. So, so we need a bit of a plan for this one. Right, so the first thing we need to do really is we need to find the acceleration of this as it comes down down and hits the ground. We're going to take gravitational constant g as equal to 10. Now, as I said, in other problems, we might actually, having using that, found that acceleration, actually go away now and say, right, okay, we will find the tension in the string. So we would apply that acceleration to one of these particles. And we know all the other forces and the accelerator and the mass, so we can work out the tension in the string. So that would be more typical. This one's not like that. So we find the acceleration until B hits the ground, coming down this slope here, and then we need to know the velocity at that point, because that is the initial velocity of particle A as it's when it's kind of pulling, when it stops being pulled by particle B. So then we need to find the deceleration of A. Well, yeah, we can see the forces, but we're then looking at what's happening to particle A as it moves up the slope. So we're then just considering particle A with its initial velocity, and we'll work out its deceleration from that. And okay, and then the fourth part, like the second part, is a bit of kinematics. Find the distance that A travels, decelerating to stop, and then we add on the distance that this has traveled down here. Now, of course, this distance down the slope is quite the same as the distance, the vertical distance, but we'll come to that. Okay, so that basically is the plan. This question is a bit of a beast. If you were to get this in an exam, then I think you'd be a trifle unlucky. And quite honestly, I think it's unlikely that you would see one like this, because it is actually quite time consuming. Right, so let's have a look. So we're going to move on here. So I've brought that diagram down here just as a reminder as to what we're doing. I think you should be able to see the main components in there. So the first thing we're going to do is consider the whole system. That's both particles, and we're going to look at the net force, and that's going to be equal to the mass times the acceleration, according to Newton's second law of motion. So if we look at that, we've got the net force acting on the system. Well, we're looking at motion down in this direction, can we be falling? So we've got mg sine 70. That's the result part of the weight coming down there, minus the friction, force of friction acting on B, minus the force of friction acting on A, and minus the result part of the weight of A acting down the plane. Okay, so that's that expression there, and that's going to equal the mass of the system. Well, both particles are of the same mass, we call that m, times the acceleration. Now we'll do a little bit of substitution and a bit of reorganization here. This FB is this minus RB, and the FA is the the FB is the minus mu RB, and the FA is the minus mu RA. We've collected these two terms together and factorized mg out of it. Then when we convert the RB and the RA, according to what we know from the diagram there and there, then we get this expression. Right, okay, we've got m's going to cancel out of there, isn't it? We're taking g equals 10. Right, okay, now I'm not going to go through all the manipulation on this. You can kind of work that through. If you're not convinced, just pause the video and just have a look at that. But it's basically going to give us an expression for A like that, and that's going to give us an acceleration of 1.292 meters per second squared, I would have written to 3 decimal places. And I had the space, but that's before B hits the ground. Okay. Right. Okay. That's the first part of the solution. Right. Second part. Now, what we're interested in now is the velocity of that particle B when it hits the ground, which will also be the velocity of A when its pulling force has kind of been taken away from it. Now that B starts off 0.75 above the ground. We've got to remember that what we're talking about is the distance along the slope. So we need to actually take that angle into account, and with a bit of trigonometry, we should be able to see that that's 0.75 divided by sine 70, which is 0.80 meters to 2 decimal places. And so that is our displacement when it comes to our kinematics. Piece of work here. So we've got the acceleration from before as well. The initial velocity was 0 because we started from rest, and we are interested in the final velocity. So for that motion, from going from rest to the ground, then we're going to use v squared equals u squared plus 2as. And if we plug in the relevant bits in there, that's going to give us a velocity along that plane of 1.44 meters per second. Right. Okay. So what's happening now is that B is moving at that velocity. A is also moving at that velocity, but A's pulling force has now disappeared because B is on the ground. It's not pulling anymore. So now A continues, continues to move, but with deceleration, according to Newton's second law of motion. And if we just write those forces in, obviously the pulling force is 0, but we've still got the resistance force of the resolved part of the weight down that 30-degree slope, and the frictional force as well. So when we substitute the coefficient of friction and the frictional force, which is this mg cos 30, we can factorize that mg because that's in all that stuff in the brackets. And this is negative. I've got a negative sign here. And that's going to equal to the mass times the acceleration. So the acceleration of that second stage, call it A2, I suppose, is going to be minus 4.86 meters per second. Right, and it continues. So obviously that's the deceleration, and that's that deceleration that is going to actually is going to erode all this velocity and till it stops. So the fourth part is a bit of kinematics where we're actually working out what this distance is, knowing that we've got deceleration of minus 4.86, acceleration of minus 4.86, an initial velocity of 1.44, so that was the velocity of particle A when B hit the ground, and the final velocity that we're interested in, which sort of momentarily comes to rest, is 0. So that looks like v squared equals u squared plus 2as, and yep, so if we plug in the relevant bits into there, we see that's going to give us a displacement of 0.213 meters to 3 decimal places. So so that's the second phase distance, but we've previously calculated the sort of first phase distance up there. So the total distance is the sum of those two, which is 1.013 meters. So that is it. So I think it's a good kind of illustration, really, not just of Newton's second law of motion and how these things are sometimes interwoven with some kinematics, but a little bit in terms of sort of problem solving and how we kind of break these things down. Not a simple problem. If you got it in an exam, say, it would be quite time consuming to do. But actually, there are no really complicated bits of this, we're just applying equations really most of the time. So yeah, it looks like a bit of a beast, but in actual fact, it's not too bad. So hopefully that has been useful, and I'll see you next time.